Hi, good morning. It's my great pleasure to be back here in Liverpool. So I'm going to be talking to you today about exploring the energy frontier, a journey into particle physics. So this is the Large Hadron Collider. It accelerates particles up to almost the speed of light before smashing them together inside of these huge detectors. The data is read out into the tier 0 at CERN, where reconstruction algorithms try to understand what happened inside of these collisions. A huge amount of data is created from these different detectors. This data, after being reconstructed, is then sent all over the planet to be analyzed. We have collaborators in every country, from Canada to South Africa to Colombia to Australia. So this is a real collaborative effort. We're an international collaboration. Our scientists are all over the world. We're not just here in Liverpool. We're not just in Europe or at CERN. We're this international collaborating, all aiming to understand the very first moments after the Big Bang. So these are the types of plots we make. The data are reconstructed, and we try and find these bumps in data to try and identify particles. So the Large Hadron Collider, 27 kilometers in circumference. It's 100 meters underground. And through these collisions, we're really trying to understand the very first moments after the Big Bang. OK, so let's go into the details. So the LHC really accelerates some of the very smallest particles in the universe. So these are protons. And we accelerate these up to up to the fastest speeds possible. So this is almost up to the speed of light. And of course, we use magnets, which we just heard about. So these magnets have to be super, super cold. In fact, they're colder than outer space. Well, they're one of the coldest places in the universe at 1.9 Kelvin. So why do we smash together protons? So protons are actually made of smaller particles, quarks and gluons. When we smash them together at high energies, what happens is part of the protons, in this case gluon, the energy from that collision, from Einstein's E equals mc squared, so the energy of the colliding protons, these two gluons in this case, go to make new mass. So this is a really important and quite strange concept. So these two gluons, the energy of their collision goes to make a new type of particle. It can be any type of particle that was present at that energy frontier at the beginning of the universe. And in this case, we have two gluons colliding together. That energy then creates a Higgs boson and also two top quarks. So why do we smash protons together at these extremely high energies? So this is a picture of the evolution of the universe. Here is the Big Bang. So at the Big Bang, all the energy and matter in the universe was at a very, very small place, a very, very small point. So it's very hard to understand how hot and how dense that could possibly be. Okay? And then the universe expanded, and as it expanded, the universe cooled down. And so just after a few split seconds after the Big Bang, particles started to form. So this is about 1 second after the Big Bang. So almost all the interesting stuff happened for us particle physicists before 1 second after the Big Bang. Just a few split seconds, particles started to form. And here, just almost up to a second, is when the quarks and gluons came together to make protons, neutrons, and other hadrons. Okay? It took another 300,000 years for the universe to get big enough and cool enough for atoms to form. So protons, neutrons to come together, and electrons. And then finally, 13 billion years later is today. So we're looking at these high energies because we want to look at these frontiers. The harder we can get the protons together, the further back in time we can study. So at the moment, at 13 TeV, tera-electron volts, we're studying a certain frontier. Okay, if we can go up higher in energy, we can look further backwards in time, further towards the Big Bang, to see what particles existed there and how the fundamental forces interacted. So why do we smash protons together at high energies millions of times a second? So why do we do it so often? Millions of times a second, you can't believe how much data that produces. Well, it's because we need a lot of data. We're trying to understand all the fundamental particles in the universe, and we're especially trying to find the rare particles. Of course, because they're rare, we haven't found them yet. Okay, so the Higgs was a rare particle. It wasn't made very often. So when building the LHC, we needed to make sure we had enough collisions to be able to create enough Higgs so that we had a large enough sample. And of course, we're looking for many new types of particles, for new physics, and they're often going to be rare. Okay, so let's look at how we do collisions. So at CERN, there's an accelerator complex. These are smaller accelerators. This is a proton synchrotron, and we're just looking at one proton and one proton at a time. Of course, there's actually beams of protons, and each bunch has billions of protons. But here we are accelerating in opposite directions in the LHC tunnel. So these magnets are used. So this goes over the French-Swiss border, I should mention. The magnets accelerate these particles almost up to the speed of light. You see, we just went from France into Switzerland. It's around 11,000 times every second this beam goes. So here's our proton. We've got 3 quarks that make up the proton and gluon. And here's our detector, this Atlas detector that myself and my colleagues here at Liverpool work on. And here the protons come to interact. So in this interaction, in these 2 protons, particles from inside the protons, quarks or gluons, smash together. Again, that energy will create a new particle, could be a Higgs boson. New particles such as Higgs or other heavy particles then decay. So all these lines are charged particles decaying from the Higgs boson. And our jobs as scientists is to to understand how the Atlas detector has interacted with all these charged particles and then reconstruct the Higgs boson and other particles. Okay, so what is it that a particle physicist does? So we ask some fundamental questions. We want to know, where did everything come from? What is everything made out of? And how does it interact? So we have very ambitious goals. So we're going to do a very quick 5-minute introduction to the history of particle physics. So we'll start with the 20th century when Lord Kelvin famously said that basically physics was over. We basically understand everything. Thermodynamics is done, classical mechanics is done. There's some issue with radioactivity we're not quite too sure about, but we're basically finished with physics, okay? He said only some decimal places to be sorted out. So of course this was not quite right. At the beginning of the 20th century, along came quantum mechanics, the study of very, very small things. Along came special relativity, the study of very fast things, and general relativity, the study of gravity. And then, of course, quantum mechanics got married with special relativity to make quantum field theory, which actually is the theory of the Standard Model, which I'll describe, which is the theory of our universe, the fundamental particles and the forces by which they interact. So back at the late 19th century, chemistry was making a very good attempt at trying to understand the universe. They identified that everything was made out of elements. So you take water, and it was made out of hydrogen and oxygen. And in fact, everything on Earth and in the universe is made out of a mixture, you won't recognize this older table, but the newer one, of any of these elements. So we had a fundamental way of reconstructing the universe. Okay, everything that you can find will be made of a mix of these different elements. However, there was a lot. At the time, they had about 80. We now know there's 118. How can we have so many fundamental elements? Is there not a simpler way to describe fundamental nature? And of course, we know now there is, the atom. So this is a much more simpler way of understanding chemistry and how things interact. There's not 118 elementary particles. Here, we had 3, protons, neutrons, and electrons, which were discovered in the beginning of the 20th century. Now we have 3 fundamental particles. That's perfect. You have different number of electrons, protons, neutrons, and you can reconstruct everything around us. Also, at the beginning of the 20th century, the photon was identified. So electromagnetism was being analyzed for a long time. And through looking at photoelectric effect, famously again by Einstein, who did a huge amount of work in the early 20th century, photons were understood to be a wave packet of light. So now we really had a good description of the universe. We know everything's made of atoms, protons, neutrons, electrons, and we have light. Is there anything else we need to describe? And then new particles started to arrive. In 1932, a positron, which is the antimatter particle of the electron, suddenly turned up. And this was actually predicted by a theorist, by Dirac in 1928. So we had this positron. We don't have any need for a positron. Why was that there? Then in 1934, neutrinos. So there's billions of neutrinos going through your body every single second. They're invisible, they don't interact very much, but they were established and detected. Why are they now here? And then muons came from these cosmic rays. This was famously said by a Nobel laureate. Who ordered that? So muons are a heavier type of an electron, exactly the same electron, same charge, but heavier, bigger mass. And then pions came along. Things were really getting out of hand. We were trying to simplify physics, have a simple way of describing things. Okay, now we're getting much more into chemistry, all these different types of particles. In the 1950s, along came the atom smashers. These are the same things as the LHC. They accelerate particles, smash them together, and try and understand what was going on with all these different types of particles. But these atom smashers didn't help anything. In fact, they found even more particles. Okay, so here they're all called Greek letters. They found sigmas, rhos, deltas, kaons, lambdas. So more and more particles were going to this what's called particle zoo. And we weren't simplifying science at all. So how was this fixed? So thank goodness in 1960 there was a big breakthrough, at least for this particle zoo. So these are all hadrons, like protons and neutrons are hadrons. In the 1960s, Murray Gell-Mann, he came up with this eightfold way to describe how hadrons are actually composed of smaller particles. So protons and neutrons are made of quarks. A proton is made of up, up, down, and neutron, down, down, up. And all these other types of hadrons are also made out of quarks. So now we had a much simpler way, again, thank goodness, of reconstructing the universe. Okay, so I'll show you the standard model in a minute, but all these other particles were then predicted by our standard model from the theory. The Boson quark was discovered. These are at Fermilab and CERN. There's the tevatron, which is another particle accelerator at Fermilab in the US. The W and Z particles, so these cause a radioactivity. This was discovered in 1983. The top particle, my favorite one, of course, and tau neutrino, and finally the Higgs. And this completed our standard model of particle physics. Okay, so here we have quarks and leptons. So these are all the matter particles. Here we have the up and the down that make up protons and neutrons. Charm strange, top, bottom, are just heavier cousins of up and down. Okay, you don't really see them day to day. You only see them in cosmic rays, particle collisions. Down here we have the leptons. So the electron we all know about, with the up and down makes our atoms. Muons and taus are the same as electrons, just heavier cousins. And then we have our neutrinos, again, billions of them going through us every second. And we have the force particles. So these are the particles that mediate fundamental interactions, the forces. This is the photon for electromagnetism, gluon that holds together the quarks, and W and Z, as I said, is for radioactivity. And of course, our Higgs boson, which gives these particles their mass. And we have no idea why the standard model works as well as it does. Okay, so we've given this in terms of particles, but actually the standard model is a theory. It's a mathematical theory. You can see it very simply written on this mug. So if you'd like to think a bit about it like a game of chess, so the particles are like the pieces of the chess, okay? They make up everything in the universe. And then our theory describes the rules of the game. It says what particles can interact. For example, if a W decays, it has to go into a lepton and neutrino. Okay, because of the rules of the standard model. Okay, it's very simple, it's on a mug. Here is a slightly longer version, and of course, this is also a simplified version of the full theory. This describes 3 of the 4 fundamental interactions of our universe. We've yet to incorporate gravity. Okay, so what are we looking for? Okay, we're trying to understand our standard model. We've been measuring these particles, looking at their different properties. But we're also trying to understand new physics, and that is looking at this new energy frontier, looking further back in time. Okay? We know there must be new physics at these new frontiers. We know there must be new physics at higher energies, and this is to do with theoretical problems like the hierarchy problem. There's also unsolved mysteries. You might have heard of dark matter, dark energy. We also have a matter-antimatter asymmetry, and we don't know very much about gravity. So I'll just finish by saying very briefly what these big issues, these big mysteries in physics are. So you can think of the universe as a pint of Guinness, one of my favorite things to drink. And And so this divides the universe into what we can see and understand and what we can't see. So only this top part of the pint of Guinness, 4% of the universe, is made out of atoms and things that we can see: Earth, stars, galaxies, dust. This is it. We only know about 4% of what the universe is made out of. 23% is dark matter. Okay? This means it's a bit like neutrinos. We know it's everywhere, but it doesn't interact, so we can't understand very much about what it is. In fact, we don't know anything. All we know is that we can't interact with it. That's why we call it dark, because we can't see it. So this is a huge problem. This makes up most of our galaxy, most of the universe, and we have no idea what it's made out of. And then there's dark energy. So dark energy is to do with the accelerating expansion of the universe. So we know the universe is expanding, but did you know that the expansion is then accelerating? So things are getting further and further away from each other, quicker and quicker. So where is all the antimatter? So this is a big problem in particle physics. At the beginning of the universe, there should have been an equal amount of matter and antimatter created. Antimatter, it's just the same as matter, but the particles have opposite charge. So positive charge, the antimatter particle has negative charge. There should be equal amounts of matter and antimatter created. And yet, everything in our universe is more or less matter. So it's a huge problem. Where has all the antimatter gone? And the last thing I'll mention is the problem with gravity. So gravity, you think, would be something we understand the best. Okay? We interact with it every day. And it's described by Newton's laws, of course, and it's described a lot more efficiently by Einstein's theory of general relativity. So it describes space-time being curved by masses. So gravity is the effect of how mass curves space-time. It bends it. Okay? That's what general relativity says, and it's been extremely well verified. Again and again, also the discovery recently of gravitational waves only goes to support general relativity's predictions. But in particle physics, we can't describe gravity. Okay? One reason is it's too weak. When we go very, very small into the world of particle physics and quantum mechanics, gravity is so weak we can't even detect it. It's almost negligible. So we can't what's called quantize it. So we have no gravity in our supposed theory of the universe, our standard model. So this is a huge problem we're trying to understand. So we have a lot to do in particle physics. We built an amazing machine, and it's running really at unprecedented rates and energies, even more than we dared had hoped. And we have thousands of scientists, engineers, and technicians all over the world, really an international collaboration of scientists, engineers, all working together to try and solve these issues. And we have tools that we never had before. We can use machine learning these days, deep learning. We have new computational tools, such as grid computing and cloud computing. And we have now cutting-edge technology, electronics and hardware. Okay, so this is really just the beginning of real particle physics. So this plot here shows the amount, so this is the amount of data we can accumulate with the LHC, and this is the years. So this is us now in 2019. We've just finished run 2 before Christmas, and we've made this much data, okay, an amount of data. Okay, we're about to shut down to implement all these new technologies and upgrade the detector, and we're going to do run 3 in a couple of years, and we're going to increase the data even more. Then when we shut down to upgrade again with cutting-edge technology, the LHC, you can see how much energy, how much more data we're going to get with run 4 and run 5. And we can really start to explore the new energy frontier and really start to understand and try and solve these big mysteries that we have in particle physics. So you can see we're really just at the very beginning. The Higgs was our first stepping stone. So it's an exciting time to be studying physics. 100 years ago, physicists thought that science was maybe complete, maybe almost done. And look how far we have come. So who knows what the next 100 years of investigation will bring. And so all these unanswered questions, these mysteries of the universe, they tell us that we've only actually just scratched the surface. We actually don't have a very good description of the universe. And there must be a deeper and more connected theory that describes matter, space, and time. There's so much more to learn. We're at the beginning of this tremendous journey. We've got thousands of scientists utilizing and developing this cutting-edge technology. And we really are on the brink of a new way of understanding matter, space, and time. So watch the space. Thank you.
That's really cool. Well done.